You have fallen into Event Horizon with John Michael Godier. Joining John in this episode is Dr. Allison Kirkpatrick. She received her PhD in astronomy at the University of Massachusetts and is a YCAA Fellow at Yale University. She's an assistant professor at the University of Kansas, and her recent work on quasars and supermassive black holes has yielded surprising findings on an entirely new class of cold quasar. Remember to subscribe to Event Horizon so you never miss an episode.
Dr. Allison Kirkpatrick, welcome back to the program.
Hi, thanks for having me back.
Now, Doctor, we have the most exciting development in astronomy in many years, finally, the launch and successful deployment of James Webb after so many years of waiting. Now, the initial science has been stunning, the images and everything else. But working with that data, what does it look like? I mean, what does the raw data, say an image or measurement, look like from JWST? And what's the process look like in getting it into something that can be interpreted?
Yeah, that's a great question. So obviously, the pictures that everyone sees on the web are press-ready pictures. When we get a science image, first of all, we don't look at it in color the way that we send it out for the press to disseminate to the public. We usually look at just one wavelength of light at a time. And then we take the multiple wavelengths and we combine them together to make color images. But when we're actually doing science, we don't use those. We just use one wavelength at a time. So all of our pictures that we look at would be in black and white, where the color just corresponds to the brightness of the light at a given wavelength, so whichever filter we're looking in. The original images that we get they're pretty messy, so they have a lot of effects in them that we have to account for, and so there's been some discussion now on how much of the early results is. Of course, there was this rush to publish papers as soon as people got their data. How much of those were wrong because the images weren't being corrected for appropriately? Because when you get an image, so you've got a couple of effects going on in your image. The first thing is that you have noise from the telescope itself. This is particularly problematic in the infrared because telescopes actually emit their own infrared light. This is one of the reasons that we wanted James Webb to be cooled, so that we could reduce that amount of infrared light. So we have a certain amount of light coming from the telescope itself, and then we just have a certain amount of noise inherent in CCD imagers. So we have to correct for that. Then we have what's called the background. If you were to take an image of the dark sky where you don't see any stars or galaxies, you would actually record a lot of light. And this light, especially in the infrared, this light is coming from many different sources. One of the biggest sources of this light is called the zodiacal light. This is caused by dust grains in our own solar system. And so we have to remove that as well. And so you do this by taking a background image, and then you have your science image, and just very simply you subtract the two. It gets a bit more complicated than that in the weeds, but that's the overview of the process. So those are the things that we've been working on.
Now, the reason James Webb is looking at infrared is because that opens up the highly redshifted earliest galaxies that we can see in the universe. And that's what you're looking at, along with cold quasars and your other work.
Yes.
Now, when looking at that, what is so far in the data, what's the furthest galaxy that we can see just from the data set as it is right now?
So, this is debatable. I don't have a clear answer for you. I'm going to argue, of course, that our team, the CEERS Collaboration, our galaxy is at a redshift of about 14. I'm going to say that's the furthest one. But there have been claims for higher redshift galaxies. The problem, again, is that these images were, again, using like the very first data reduction, and that first data reduction wasn't so good, and it turns out that some of the red band magnitudes, so some of the red light might have been overestimated, and some of the blue light, so light coming in from the bluer filters, might have been underestimated. And that can change basically the shape of what's called the galaxy's spectral energy distribution. So this is how we find these really high redshift galaxies. So we are looking to see, is a galaxy brighter at certain wavelengths than in other wavelengths? Because if we see a galaxy that is not bright at short wavelengths of light, so towards the bluer end of the near-infrared spectrum, but it is really bright towards the redder end, that tells us that that galaxy is potentially located in the very, very early universe, because we're looking for certain breaks in the spectrum that are produced by very young stars. And so if you have incorrect calibrations on your red and your blue light images, then you can erroneously think that you found galaxies at really high redshifts, and that might not be correct. The other thing that makes it really hard to identify galaxies at really high redshift is because these early galaxies, their spectral energy distributions also happen to look just like galaxies that aren't at such high redshifts. So maybe redshift of 2 to 5, but have a lot of dust in them. And so for example, for one of the really high redshift galaxy candidates that was reported a couple of weeks ago, our team came back and argued that no, this is a redshift of 5 galaxy. It just has a lot of dust in it. And that can be tricky, and people are debating that.
Now, by looking at one of these ancient galaxies that are apparently just a few 100 million years after the Big Bang, when you're looking at these, do the spectra differ? I mean, do you see what's consistent overall in a galaxy with just a bunch of population 3s type stars, or do we just not have that ability when looking wholesale at a galaxy?
Okay, this is another great question about something that is also being debated right now. Hot debates happening. The answer is, right now, we don't know. So currently, we don't have spectra of the earliest galaxies, which make it really hard to identify the gas, what the actual gas components are. We just have photometry, so we just have measured the brightness of galaxies at different wavelengths. Okay. People have applied models based on closer by galaxies and estimated the stellar mass of these earlier galaxies, right? That's one of the first things that you can do, is you can fit a model of how a certain population of stars would emit at each wavelength, and you can fit that to your galaxy photometry, and you can say, okay, that means that this galaxy must have this many stars. So that has been done, and what has been found is that these galaxies are really massive, like surprisingly massive, and possibly too massive to have formed this early. That doesn't mean that something's wrong with our theory. It could actually be that something's wrong with our models, that we're using the wrong models, because we're modeling it based on POP1 and POP2 stars that we understand really well, rather than POP3 stars, which are purely theoretical at this point, and we haven't empirically measured their emission. So that's something that I think will change.
We have the elephant in the room here, which was recently apparently imaged, I saw it on Twitter, of Arundel, a gravitationally lensed star from a distant galaxy that might be a population 3.
Yeah.
What are the chances, you think?
James Webb was going to find them. So I think it's good. I'm excited about this. I would be surprised if it is an individual star. I think more of the predictions were that James Webb would be able to find star clusters of POP3 stars, because stars always form in clusters. And so I think it would be more likely, it'd be easier to see a few hundred POP3 stars together rather than one individual one.
It's worth noting exactly how distant this is because of the expansion of the universe. When you look at a star like Arundel or any gravitationally lensed star like that, or the star clusters, you are looking across more space than the age of the universe, essentially. 22 billion light years, something like that. And it's just astounding how distant these things are.
Yeah, so that's That's really good to remember. We're actually, distance-wise, it gets a bit wonkier than that. So we talk about it just in terms of the age of the universe. I think that's the best way to think about it, because the actual distance would be a lot larger than like 13.7 billion light years, because the universe is expanding as well. I don't remember what the calculation is off the top of my head, but I think it's closer to like 50 billion light years is the size of the universe.
It's absolutely astonishing. Now, what is the CEERS Collaboration? What are the goals, and what are you guys looking for?
Yeah, so we were one of the lucky few teams chosen to have our program executed first on the James Webb Space Telescope. So our collaboration, it stands for Cosmic Evolution Early Release Science, and it is headed up by Steve Finkelstein, UT Austin, and I am on the leadership, I'm on the executive committee of this, and we were awarded a little bit over 50 hours. So James Webb solicited these programs that would run during the commissioning phase. So we would get our targets observed first. The catch was that the data wouldn't be proprietary. So normally, because writing a proposal and coming up with new ideas and selling it, that's a lot of work. So normally what happens if you get awarded time on a telescope is you get a year with your data before anybody else can have it. So, but we weren't granted that, and that's okay. Our goals were basically to test all of the observing modes, because the amount of things that James Webb can do is just insane. It can do both imaging at short wavelengths and at long wavelengths, but it can do spectroscopy. And not only that, it can do spectroscopy at each pixel on an image. So rather than just getting one whole spectrum of a galaxy, you'd actually get a whole bunch of tiny little spectra, like at each pixel located within the galaxy. And so we set out to test a lot of these modes, and we have a few goals. One is that we are looking for the earliest galaxies. We think we found one, so that's great. Another one, the part of the science that I'm helping to lead, is looking for more supermassive black holes in these galaxies, trying to find supermassive black holes within galaxies that look like our Milky Way 10 billion years in the past. And that's something that we've never had the capability to do before. And so that's the data that I'm digging into. And what we really want to understand is when black holes grew the most and how they impact their host galaxies. We're also trying to understand how the shapes of galaxies evolve. And that's been a real revelation with James Webb, is that we're seeing that these galaxies have these amazing disk-like structures that we didn't think of before. And they have it like way earlier than we thought. So that's another big focus of our collaboration is understanding when galaxies got their shapes and how those shapes changed over time.
So this almost seems like galactic paleontology. You're looking at a fossil Milky Way, showing it at a much earlier time. Now, you see these disks, but do you see any structure yet?
Yes.
Of the formation? Really?
Yes. They look like, some of these things look like you took the Milky Way and you put it back 10 billion years ago. You can see it like it just spiral arms, and you can see just bright spots of star formation throughout the spiral arms. It's really incredible.
Now, you definitely are obviously seeing clearer, more heavy star formation in these. Now, are you seeing anything like a quasar yet that early?
I just looked at our data today, and no, but I didn't expect to. The reason is, so James Webb is not going to be good at finding quasars. The reason is that quasars are the most active, most luminous black holes, some of the most luminous objects in the universe. That means they're incredibly rare. And so to find them, you have to look at a large area of the sky. So one of the limitations of James Webb is that it is not a survey instrument. It is not going to do it's not going to look at large areas of the sky. So it is not going to find these rare, bright things. But we have other telescopes that can do that. Instead, what it's going to do is basically study in more detail than has ever been possible before galaxies that are more normal. And it's going to tell us how the lower mass and how the normal galaxies evolved, which is something that we don't know.
Now, in regards to supermassive black holes, now this early, there's been some suggestion that maybe the seeds for galactic supermassive black holes were primordial black holes formed at the, just shortly after the Big Bang. Now, could that shed light on that? I mean, could we get an earlier picture or view of what the environment, at least, of a supermassive black hole in a very early galaxy would look like?
Yes. So this is another goal. I think this one's going to take a bit longer. I think we're going to need to observe more areas before we're actually able to do this, because again, these events would be rare. But so the most likely way, so there's a few formation scenarios for black holes, for supermassive black holes. One of them is that it's a pop-3 star that collapses and forms a black hole, and then that black hole keeps merging with other black holes to keep growing. That scenario is looking less and less likely because it's really hard to form quasars very quickly, and we do see quasars at high redshift, like redshift 7. So it's hard to get a quasar by redshift 7 if you do it that way. The other suggestion, there's two more, primordial black holes, is that these are something left over from the Big Bang, and so they've been kind of growing continually ever since. And then also direct collapse black holes. And direct collapse black holes is where you have a cloud of gas. It starts collapsing down, but it is so massive that it is unable to stop the collapse with fusion. And so it doesn't really become a star, it just keeps collapsing down into a black hole. Direct collapse black holes is the favored scenario right now. They have certain signatures, and so it is possible, if we survey enough of the early universe, that we can actually identify a direct collapse black hole. And so that would be really cool, and that would essentially be proof of that scenario. But you're right. Every time we find an early black hole, it's troubling to understand how it got there and got to be so big.
Now, direct collapse black holes, that's spooky. Something that just came out of an enormous amount of dust and gas and didn't have a progenitor star.
Yeah, that's right.
Created spooky early stuff in the universe. Now, would such a thing, having so much material available to it, just immediately form an accretion disk and look like a classical black hole just out of nowhere?
I love this question. Yeah, probably. It probably would, because that would be kind of the signature that we're looking for. The other signature that you can, the other way to find the seeds of black holes is to get a gravitational wave observer, not LIGO. LIGO won't do this. It's not the right part of the gravitational wave spectrum, but LISA. LISA is going to be launched in the 2030s, and that could basically detect the mergers of smaller black holes in the early universe, and then you could back out the mass of the black holes that are merging together. That will kind of tell you formation scenarios. But yeah, the direct collapse black hole. So basically it should collapse down, and you should get something that's about 10,000 times the mass of the sun. So then all of the gas that would be left around it would form an accretion disk, and then the idea is that this thing would just kind of be free floating until it falls into the center of a dark matter halo that also has a galaxy at the center, and then the black hole will just naturally settle at the center of the galaxy because that's where the gravitational potential is. And that's how galaxies got their black holes.
Amazing. Now tell us about Maisie's galaxy.
Yeah, this is our Z of 14 candidate. This one was really exciting. So when we identified it, not when we put out the paper, when we identified it, it was the highest redshift galaxy known. We put out our paper like the same night that everybody put out their papers with a whole bunch of high redshift candidates. But we think ours is more secure, and we've been able to rule out now that it's not a dusty candidate at lower redshift because we have longer wavelength imaging where we can go really look for cold dust in this galaxy. And so we haven't seen that. Based on the image calibrations, we could be seeing this thing shift down to redshift 12 rather than redshift 14. That's still okay. But what is really exciting about this galaxy is that we've been able to measure a stellar mass for it and a star formation rate. And it's a real bitty star formation rate, but this galaxy is outside of the scope of basically galaxy formation models. So galaxy formation models will predict how many galaxies of a certain stellar mass or brightness you should have by a given redshift. And so you can compare how many you find with the galaxy evolution models and then tweak the models, basically. And this galaxy, according to like a whole suite of galaxy formation models, really shouldn't be there. And so that's really exciting because that introduces some tension. And again, it's early days, so there's still a possibility that it's measurement errors, but there's also a possibility that there's this missing ingredient into how galaxies form that we don't understand because we're not the only team finding these massive galaxies early in the universe. And so there could be something new about the universe that we're going to learn.
There's nothing like a good discrepancy.
Yes. Yes, that's right.
Does this have any implications? For example, say you test the models and it just keeps coming up that these galaxies shouldn't be there. Is it possible that there could be a revision to the Big Bang from this as far as dates go?
Okay, so yes, that is one possibility. The other possibility, the more likely possibility, is that we really don't understand dark matter really well. Because dark matter, so the way that we think the galaxy formation occurs is that the dark matter forms first and it clumps first into these large halos, and then it gets enough gravity that the baryonic matter, the stuff that forms galaxies, streams into the center of these huge dark matter halos and starts forming stars and galaxies, and they pretty much form simultaneously. And so you have to have enough time for the dark matter halos to evolve to be massive enough to have the galaxy matter stream inside of it. So there's probably something there that we don't understand, because again, we don't even know what dark matter is, right? We haven't identified a candidate. So that's the most likely thing, is that we're just going to have to rethink what is dark matter and how does it attract itself, and how can that process happen more efficiently than it currently does in models.
So that really figures very heavily nowadays in thinking about how galaxies form, is what exactly is the dark matter doing. But that's got to be confounding because we just don't have enough information on dark matter yet.
Right. Yeah.
Now, will this yield information? Now, by studying these very distant galaxies and the effects of dark matter that early, that seems to me to be fertile ground for yielding clues on the nature of dark matter, wouldn't you think?
Sure. And there's some speculation. I will say that I think it's considered to be more on the fringe, but there's certainly speculation that it could be the nail in the coffin for dark matter. Maybe we don't have dark matter at all. I wouldn't go that far, but who knows what will happen.
Well, there does seem to be a whole lot of observational evidence pointing towards the existence of dark matter. I find it compelling myself that this is real, whatever it is. But then again, I mean, in itself, dark matter's, sort of fringe, an invisible,
right?
An invisible form of matter, non-interactive form of matter that seems to be controlling the movement of galaxies or the formation of them thereof.
Yeah.
And maybe even what part does it play in star formation and things like that? So it's so many open questions regarding dark matter. What's next on the list for your team? What do you have a list of candidates and targets to look at as far as very high redshift galaxies, or are you just looking through images being taken to try to identify them, like deep field images and things like that?
Yeah, so with our candidates, we are trying to follow up because the gold standard to pin down a redshift is you have to have spectroscopy and you have to identify an emission line. And so we are writing follow-up proposals to try to get spectroscopy on our high redshift candidates. For me, right now, I'm busy analyzing our data from the MIRI instrument, trying to pin down exactly how many black holes we have in these images that we didn't know about before, and not only that, but their accretion rates. So how fast they're growing. And then the next big thing that we're all doing as a team is we are also morphologically classifying all of the galaxies. So looking at the images, deciding if it's a merger, deciding if it's not a merger, deciding if it has a disk. And so that takes a bit of time, and everyone gets to look at the images and offer their opinion. And then we can say something about when galaxies develop their disks.
Now, just out of curiosity, looking at the structure of these early galaxies, when we look at the closer galaxies, we see elliptical galaxies, huge ones. And we think, through merging galaxies, star spirals and things like that, the end result is an elliptical galaxy. So are these elliptical galaxies that we see that are closer, were they that way because they merged very early on in the early universe and became elliptical far earlier than most?
Okay, so there are two things happening here. So first, yes, that is one formation process for ellipticals, is that two gas-rich disks collide and they go through a burst of star formation, and then all of the orbits of all the stars are now disrupted because in a spiral galaxy, stars orbit around their center in a plane and all like in the same direction, much like planets orbit around our sun. And in elliptical galaxies, stars are just going crazy every which direction. So that is one thing that does it, is merging. However, we also see ellipticals really, really, really early. Basically, as soon as you see galaxies, you start to see an elliptical galaxy. Maisie's galaxy could be an elliptical. That is likely due to how the galaxy formed. So galaxies that formed spiral galaxies would have formed in less dense environments. So dark matter halos that weren't as massive would not have attracted as much gas. And so it would have taken longer for that gas to funnel through the dark matter halo and settle into a galaxy. Well, that slower process can allow the gas to settle into an accretion disk, or just a rotating disk. And from that rotating disk, stars can form. When you have a gas cloud collapsing down, that's what nature prefers, just due to conservation of angular momentum. However, if you're in a really dense environment, you got a lot of gravity, you're in a bigger dark matter halo, then your gas may have collapsed fast enough that it wouldn't have had time to form a disk, and you just started out life as an elliptical galaxy, a really compact elliptical galaxy.
It's amazing how dynamic it was.
Yes.
A lot was going on back then. All right, Doctor, thank you for joining us today. And I look forward to the continuation of your work and maybe checking back in again sometime.
Yeah, that would be great. I'd love to come back.
Event Horizon and my channel are now available as a podcast on Apple Podcasts, Spotify, and YouTube memberships. Early ad-free episodes, bonus episodes, and sleep-focused content. Sign up now by clicking the links below to your platform of choice.